What's going on, everybody? Mr. Diamond back again, and we're picking up the notes where we left off. We just did projections, so we're going to come back to stereoisomers now. And I've got my molecule kit again, and again, I have no forethought in preparing these things ahead of time, so I'm going to go ahead and I'm going to make one of these pictures right up here. So these don't have double bonds on them. And I'm going to go ahead and just try to make the one on the left. So I've got my hydrogen going up on the same flat 2D plane. I'm going to use this green to represent my fluorine. I'm going to use red to represent my bromine. So I'm facing this direction. So I want it to be coming out at me, because if you notice the wedge here, that's telling me the bromine is coming out. So I need that to be there. And then I'm going to use this little silver one here to represent my chlorine. So this is a strategy you're going to probably have to use for this section. Is you may have to color associate certain pieces of the molecule. I usually have a couple of pens that are the colors of the molecules I have in my kit, and I use them to actually identify them on the structure, so I just know what they are. So I've got hydrogen, hydrogen. I've got fluorine right here. I've got bromine. I guess I should flip this so it's pointing towards you. I've got bromine coming out. I've got chlorine going back. Now what I'm going to try to do is I'm going to try to take this shape and I'm going to try to make it line up with the one over on the other side. And looking at the stuff, it's made out of the same pieces, so it feels like it should be kind of easy, but you'll notice that when you rotate it and when you try to get it to line up, bromine is facing the opposite direction. It's going in instead of out, and chlorine is coming out instead of in. So they look really simple, and they feel like they should be the same thing, but you can't actually get them to line up with each other. When you build these, you realize they seem identical, but they're not. They're mirror images of each other. When we have something that is a non-superimposable mirror image, and what I mean by that is it's a mirror image that you can't rotate and twist to get it to go over the same molecule, we call that enantiomers. So again, if you notice here, this and this look the same, hydrogen, fluorine, chlorine, bromine, hydrogen, fluorine, chlorine, bromine, but they're actually just mirrors of each other. Everything is pointing on this side, the chlorine's out, the bromine's in, the bromine's in, but they're inverted from each other. So you can't, even if you rotate them 180 degrees, you can't get them to go over each other. So you can probably see, this is where you're really going to need molecule kits. It can be hard to tell apart multiple structures by just looking at the page. So like these structures, for example, are the same. They might not look like it, but they're actually the same structure. You can actually rotate this one, and let's try to prove that really quick. So I've got, from this angle here, I've got my hydrogen, my fluorine, my bromine is going backwards, my chlorine is going forwards. If I just twist it this way, I now have my bromine coming out, my chlorine going back, my fluorine to the side, my hydrogen right there. It's the exact same shape, even though it looks kind of like it's set up the same way as the other one. So what if we have identified that two molecules are put together in the same pattern, but they're not superimposable? Well, if they're not superimposable and not mirror images, so like these guys right here, we would call them diastereomers. So in this case, the difference between that last molecule back here is that it was, or if I go back 2 pages, we've got chlorine out, bromine in, chlorine out, bromine in. So they lined up. Over here, we've got chlorine in, bromine out, chlorine out, bromine out. They're both facing outwards or inwards the same direction. So that means they're not going to be able to be superimposed over each other. You're not going to be able to just rotate them and get them to line up. So they would be diastereomers. The difference between these can get a little confusing, especially now that we have all the other isomers from last chapter as well. The easy-ish way of kind of dealing with this is, are they different conformations of the same molecule? If yes, they're conformational isomers or conformers, that means they're not actually isomers. They're just like this thing right here, our anti-gauche, those things right there would be conformational isomer or conformers. I'd rather you use the term conformers or not use a term at all, because I don't want you to get the term isomer confused with it. If they're different conformations of the same molecule, then they're isomers. If their connectivity is not the same, they're constitutional isomers. You just have things attached at different points. If their connectivity is the same, they're stereoisomers. If it's a double bond involved, that's a geometric isomer. If they're non-superimposable mirror images, they're enantiomers. If they're non-superimposable non-mirror images, they're diastereomers. And again, if they're identical, they don't count as isomers. One thing you notice that these situations really, they require you to have a carbon that in some way can be mirrored and can have something that actually can be different. And this will only occur if you have 4 unique groups attached to a carbon. We call these carbons with 4 unique groups bonded to them chiral, which comes from the Greek word for hand. Technically, the definition means having no plane of symmetry, but 4 unique groups is the easiest thing to identify. So if we go back here, the diastereomer we had here actually had 2 chiral centers, or 2 chiral carbons. That's part of what made it non-superimposable, was that this one was going one direction, this one was going another direction, and these two both were going the same direction. Those are both chiral centers on their molecule. So a question that you could get asked before we do any real naming stuff would be like this, just identifying all the chiral carbons in the below molecule. So here's what you want to do. You want to find, you get to ignore anything that's double bonded, anything that's triple bonded, anything that's not a carbon. And you're just going to be kind of going through and finding, are there any points where a carbon is bonded to, it either needs to be bonded to 4 things directly on the page, or be bonded to 3 things, because then the 4th thing would be a hydrogen. So for example, if I go down like here, this carbon is bonded to a carbon that's attached to this piece of the chain, a sulfur that's attached to this piece of the chain, and then a carbon that's attached to this piece of the chain. Now, even though those are both carbons, this chain is different than this piece right here. So that's 3 unique things. There would have to also be a 4th hydrogen right there, so that would be a chiral carbon. Same with right here, same with right here, because again, that's unique, that's unique, that's unique. And I know that these are both carbons, but again, this carbon is attached to different things and will have slightly different properties than this carbon because it's attached to a sulfur. This can't be chiral because it's double bonded to something. This isn't chiral because it's got 2 hydrogens here. Same with this one, same with this one, same with this one, and same with this one. So we've got 1, 2, there are 3 chiral carbons in this molecule. Now, you can use chiral carbons to predict information about molecules. Compounds without chiral carbons are usually achiral, which means they don't have any planes of symmetry, but that's getting beyond what we actually care about for this class. Compounds with 1 chiral carbons are chiral, and that usually means that should mean they can form enantiomers. Compounds with more than 1 chiral carbon are chiral and can usually form diastereomers. You can also predict how many stereoisomers a molecule will have. To predict this, we use what's called the 2n rule, where n is the number of stereocenters. So, for example, if there is 2 chiral centers, there should be 4 stereoisomers, because 2 to the 2nd power is 4. And you can kind of think of it as this one could be one direction, the other direction, and then one direction. Like, okay, we'll call it left and right just for convenience sake. It's not really left and right. It'll make more sense in examples when you work them out. But if you, for example, had 2 positions that could be either left or right, you could have left, left, right, right, left, right, right, left. Those are all of the 4 possible options. If you had 3, left, 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 right, 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 left, left, right, 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 left, left, right, 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 left, left. Yeah, whatever. Anyway, as you add more centers, there's more possible options that you can have. So it's 2 to the power of however many stereocenters there are, either geometric or chiral. So it also could be, there could be a double bond that has an EZ configuration or a cis-trans configuration, and there could also be a chiral carbon, and that could also be affecting your stereoisomer count. So looking at these guys, we can have the question, are these molecules chiral? So this carbon right here is bonded to 4 things. It's got 4 things connected to it, but this piece is exactly the same as this piece right here. So our answer would be no, they are not chiral, because this identical piece and this identical piece mean that there is not going to be one specific direction or orientation that these things are being built. Coming over here, we've got a carbon here, but that's attached to 2 identical things. This carbon here is attached to 2 identical things. Those are double bonded. But right here, and right here, we've actually got this carbon's attached to an oxygen, this side of the chain, and a unique different side of the chain going around this cyclo, this cyclic portion of the molecule. This one right here is attached to a nitrogen, the cyclic part, and then a cyclic part down here. This one here is one side of the ring, a second different side of the ring, and then another unique carbon chain. So there's actually 3 chiral carbons in this one. Those 3 chiral carbons means that, number 1, it is chiral, and that also means that there are 2 to the 3rd, so there is 8 possible configurations of stereoisomers for this carbon. Actually, there'd be even more. This one would have to be cis because it's in this double bond, or it's in this ring here, but this one's actually another portion that could be considered for stereoisomerism because it could be cis or trans. So there's actually 1, 2, 3, 4 possible positions. 2 to the 4th power is 2 times 2 times 2 times 2, which is 16 variations of this molecule that could exist just based on how things are positioned in 3D space. So for indicating chirality, just like our other stereocenters, we're going to use what is called, where we used EZ labels, we're going to use what's called Ka-Ingold Prelog rules to determine the handedness or the chirality of a carbon. Handedness is labeled with either R configurations or S configurations. So how this works, number 1, you number each substituent attached to the chiral carbon from 1 to 4, 1 being the highest atomic number, 4 being the lowest. Hydrogen should usually be your lowest, and you follow the same priority rules as EZ, where like if it's tied, you go to the next thing and the next thing until you get something that's different. Number 2, position the molecule so lowest priority is pointing away from you, leaving the other 3 groups fanning out from the center. Number 3, rotate so the highest priority group is on the top, and then you're going to draw a circle 1, 2, 3, from 1 to 3. And then that will tell you if it's going clockwise, that it's R configuration, or counterclockwise, it's an S configuration. Now those rules are really weird. They probably are going to take like quite a bit of time for you to really be able to grasp. But I'm going to do these examples in a separate video so I can actually use my molecule kit and show you how it'll work, and it'll make a lot more sense. That'll bring us to the end of this video. I'd say I hope that makes sense, but I know this stuff is a little bit confusing, so I wouldn't blame you if you feel a little bit confused. In the meantime, though, this is Mr. Diamond. If you have any questions, let me know. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.